Sometimes, if you touch a metallic doorknob or any metallic object, you might experience a mild shock. This is because the metallic object was charged, or in other words, it carried an electric charge. Objects that carry an electric charge are said to be electrically charged. We know that when a comb is rubbed against dry hair, it begins to attract small pieces of paper. When two pieces of silk cloth are rubbed against two glass rods individually, and the glass rods are kept beside each other, the glass rods repel each other. Now, if one of the silk cloths and a glass rod are kept beside each other, they attract each other. Now, bring one charged glass rod in contact with a pith ball and then separate them. Then bring the other charged glass rod in contact with other pith ball and then separate them too. When these pith balls are kept close to each other without contact, we observe that they repel each other. The physical quantity responsible for all these phenomena is known as electric charge. Electric charge can be defined as the property of matter that exhibits its electrostatic interaction with other matter. From previous examples, bodies like combs, glass rods, silk cloth pieces, pith balls, etc. are said to be electrified or are called charged bodies. The study of electric charges at rest and the physical quantities associated with electric charges at rest is called electrostatics or static electricity. These experiments prove that a body can be charged by rubbing against another body or by simply bringing a charged body in contact with another uncharged or neutral body. When the glass rod and silk cloth were first rubbed, they get electrified. But when they are brought in contact again and separated, they lose their electrification or charge and are neutralized. In other words, the charge on them is nullified. Hence, we can conclude that one of them may be positively charged and the other negatively charged when they are rubbed against each other. From these observations, we see that there exists only two types of electric charges in the nature. Conventionally, they are called positive and negative. It is also observed that the like-charged bodies repel each other. For example, two pith balls, both carrying like charges, repel each other. Unlike charged bodies attract each other. For example, a pith ball carrying a positive charge will attract a negatively charged pith ball. We know that all matter is made up of atoms or molecules. Also, within an atom, the total negative charge is balanced by the total positive charge in it. When we rub one material against another material, the material in which electrons are relatively loosely bound to its atoms readily loses a few of its electrons to the other material. the material that lost electrons now has a deficit of electrons and hence becomes positively charged. And the one that gained electrons becomes negatively charged. In this case, the glass rod lost electrons and became positively charged, and silk gained those electrons and became negatively charged. To know whether a body has been charged, we use an instrument called a gold leaf electroscope. It consists of an insulated metal rod with 2 gold leaves or foils at one end and a metal disc at the other end. This setup is enclosed in a glass jar with the help of a tight cork with the disc placed out of the jar. To test a material like a glass rod for electrification, the object should be brought in contact with the metal disc of the gold leaf electroscope. The contact should be momentary. If there is no change observed in the position of the gold leaves, it indicates that the glass rod is uncharged or is neutral. If the gold leaves repel each other, then it indicates that the glass rod is charged. The amount of divergence provides a rough measure of the charge on the glass rod. Assuming that the glass rod was positively charged, the gold leaves now carry a positive charge. Now, if we touch the metal disc with the silk cloth used to rub the glass rod and take it away, we observe that the gold leaves fall back to their original position. Thus, we can say the silk cloth was negatively charged. On contact, the opposite charges on the gold leaves and the silk cloth nullified each other. We know that electric charges are conventionally called positive and negative charges, and that like charges repel each other and unlike charges attract each other. However, if the size of charged bodies is very small, but the distance between them is comparatively larger than their sizes, such charged bodies are treated as point charges. Coulomb, C, is the SI unit of electric charge. However, smaller units such as microcoulomb and millicoulomb are also used in electrostatics. Electric charge is a scalar quantity, which has only magnitude but no direction. Hence, the total charge on the body is equal to the algebraic sum of the individual charges given to it. Let us illustrate this with an example. Consider a body carrying a charge, say Q1. We add another charge Q2 to this body. Now, the total charge on the body is the algebraic sum of both charges. That is, total charge Q is equal to Q1 plus Q2. Similarly, if a body carries n number of charges, Q1, Q2, and so on up to Qn, then the total charge on the body Q is equal to Q1 plus Q2 plus Q3 and so on till Qn. While adding the charges, proper signs should be used. A positive sign for a positive charge and a negative sign for a negative charge. We can determine whether a body is charged positively or negatively by finding the algebraic sum of all charges on the body. For example, if a body is given 6 charges, all in coulomb, say +1, -2, +3, -4, -5, +6, the algebraic sum would be -1 coulomb, which means it is a negatively charged body. Another property of electric charges is that the total charge in an isolated system is always conserved. When a glass rod is rubbed with a silk cloth, electrons are transferred from the glass rod to the silk cloth. Now, both the glass rod and silk cloth are charged. Here, there is only a transfer of charge taking place. Neither is a new charge created, nor is any charge destroyed. The number of electrons lost by the glass rod is equal to the number of electrons gained by the silk cloth. If we consider the glass rod and silk cloth as an isolated system, then the total charge of this system before and after rubbing remains the same. Therefore, we can conclude that the total charge of an isolated system is always conserved. Similarly, charges are also conserved in natural processes such as the beta decay of a neutron. During the beta decay, a neutron breaks into a proton and an electron, releasing a neutrino. Here, the neutron and neutrino are chargeless particles, while the proton and electron are oppositely charged particles, whose combined net charge is 0. Hence, we observe that the total charge in this process is conserved. The charge on an object is measured as an integral multiple of the basic unit of charge that the proton or electron carries and is denoted by E. This property is called quantization of charge. The magnitude of the basic unit of charge E is approximately equal to 1.6 into 10 raised to power minus 19 coulomb. In an atom, when we refer to the charge on a proton, its value is positive and is referred to as plus E, whereas the value of E for a charge on an electron is negative and is referred to as minus E. Thus, the charge on an object Q is equal to the product of the number of electrons gained or lost by it, N, and the basic unit of charge, E. Now, let us calculate the number of electrons 1 coulomb of negative charge carries. Consider a body possessing a charge Q equal to minus 1 coulomb. Let the number of electrons it has gained to become negatively charged be N. As the charge Q on a body is quantized, we have Q equal to NE, where the basic unit of charge E has a magnitude of 1.6 into 10 power minus 19 coulomb, and Q equal to minus 1 coulomb. Substituting the values of Q and E and simplifying, we have N equal to minus 6.25 into 10 power 18. Here, N is a negative integer, indicating that the body has gained a negative charge. So, we see that 1 coulomb of negative charge contains 6.25 into 10 power 18 electrons, which is a very large number of electrons. In the practical examples we have seen for charging a body, we deal with bodies possessing a charge of about a few microcoulomb. the charge of microcoulomb, that is, 10 to the power of -6 coulomb, is very large compared to the basic unit of charge E. When such a microscopic level of charge is involved, the concept of quantization of charge can be ignored, since it has no practical significance, where we say the charge is always added or removed in integral multiples of the basic unit of the charge. Quantization of charge is significant only in the microscopic sense, when the charge possessed is due to a few hundred times the basic unit of charge E, or even less than that. Let us now learn about conductors and insulators. We know that atoms are the basic building blocks of all matter. In an atom, the protons and neutrons are the constituents of the nucleus, while the electrons revolve in orbits around the nucleus. For some materials, generally metals, the electrons in the outermost orbit are loosely bound to the nucleus, and these electrons are called free electrons. These electrons are relatively free to move around the material. Such materials with a large number of free electrons are called conductors, and as such, these materials readily allow the flow of electric current through them and cause very little resistance to the flow of electricity. Metals like copper, nickel, and the human body and earth, etc., are some conductors. Some materials have a very small number of free electrons, and hence offer very high resistance to the flow of electricity through them. Such materials are called insulators. Non-metals such as porcelain, plastic, glass, wood, and nylon are some of the best insulators. It is advisable to wear rubber footwear or gloves or stand on a wooden platform while handling electrical equipment, since they are insulators and protect us from the harmful effects of the electric current. In the absence of the gloves, any leakage in the current from the electrical equipment is transferred through the body to the earth, and this is known as grounding or earthing. In any household electric circuit, in the mains supply, we see 3 wires, namely live, neutral, and earth. Live and neutral wires carry the electric current, whereas the earth wire is used as a safety mechanism. All earth wires terminate in a thick metal plate buried deep in the earth. When a fault occurs, or the live wire touches the metallic body of an electric instrument, the charge immediately and safely flows into the earth because of the earth connection through the earth wire. This prevents damage to human life and property. There are 3 methods to charge a body, namely charging by friction, conduction, and induction. Let us first look at charging a body by friction. When 2 uncharged or neutral objects made of different materials, say a glass rod and a silk cloth, are rubbed against each other, both objects get electrified due to a transfer of charges. This process is called charging by friction. When rubbed, the glass rod loses a few electrons to the silk cloth. This deficit of electrons on the glass rod makes it positively charged, and the excess of electrons makes the silk cloth negatively charged. In this method, there is a transfer of electrons from one body to another. the material that gains electrons is negatively charged, and the one that loses electrons is positively charged. In this case, silk is negatively charged and glass rod is positively charged. Let us now look at how a body can be charged by conduction. If we momentarily touch the positively charged glass rod to an uncharged pith ball, the pith ball becomes positively charged too. This process of charging by bringing a charged body in contact with a neutral body is called charging by conduction. In this case, some electrons are transferred from the pith ball to the glass, and thus the glass becomes less positively charged by gaining the electrons. We observe that both bodies involved in this method of charging by conduction acquire the same type of charge once the process is complete. Let us illustrate this by a numerical example. Let us assume that initially glass has a deficit Ng of 200 electrons. Using the quantization of charge principle, that is, Q is equal to Ne, we see that the charge on the glass is Qg equal to plus 200E. Now, when this glass rod was in momentary contact with the pith ball, let us assume that because of the electrostatic attraction, a few electrons, say Npg equal to 50, are transferred from the pith ball to the glass rod. Now, the pith ball has the deficit Np of 50 electrons, which implies that the charge on the pith ball, Qp, is equal to plus 50E. Similarly, the glass now has a charge of plus 200E minus 50E, where minus 50E is the charge due to the 50 electrons gained by the glass. Therefore, the effective charge on the glass is plus 150E. Hence, it has become less positively charged compared to its original state. We can also charge a body without contact, as in the first two methods. The third method to charge a body is induction. When a charged object, A, is placed near an uncharged object, B, object A induces an unlike charge on the near side of B and a like charge on its far side. In this case, the charges inside B are only polarized and no transfer of charges takes place. This process of polarization of the charge on an uncharged body, when a charged body is held close to it, is called induction of charge. For example, bringing a negatively charged rod near a neutral metal sphere will induce a positive charge on the near surface of the metal sphere and a negative charge on the far side. When the negatively charged rod is brought near the metal sphere, a few free electrons in the metal sphere move away to the far side of the metal sphere due to repulsion, leaving a positive charge on the near side. This charge is temporary. That is, if we move the glass rod away, the sphere returns to its original uncharged state. When the negatively charged rod is held close to the metal sphere, the charges in it are polarized due to induction. Now, if we earth the far side of the metal sphere using a conducting wire, the electrons on the far side of the metal sphere flow into the earth. However, the positive charges on the near side of the metal sphere are held at rest by the negatively charged rod. Now, if we take away the glass rod from the sphere, the positive charge on the metal sphere distributes uniformly across the sphere. In this way, we can retain the charge on the metal sphere. In the method of charging by induction, we observe that the induced charge is always equal to the inducing charge for a conductor. Now, we keep two metal spheres, A and B, supported on insulated stands, in contact with each other. When we bring a positively charged glass rod near sphere A, negative charges accumulate on its near side, and positive charges accumulate on the far side of sphere B, according to the principles of attraction and repulsion respectively. Now, separate the spheres by a very small distance, keeping the charged glass rod near them. There will be a force of attraction between A and B. Then, if we move away the glass rod, sphere A will retain the negative charge, and sphere B will retain the positive charge. We observe that the excess charge on the metal spheres distributes uniformly later. Coulomb's law, stated by Charles Coulomb, a French physicist, to find the electrostatic force of attraction and repulsion between two charged particles. This law was defined after an extensive study of force between the charges using a torsion balance. A torsion balance has an insulating rod with a metal-coated ball at one end and a balancing sphere at the other. This rod is suspended with the help of a suspension fiber. The graded circular scale gives a measure of the displacement of the sphere due to repulsion. Another static sphere, which is identical in size to the metal-coated ball, is placed at the zero mark. A micrometer screw at the top helps adjust the distance between the free and rotating spheres. The static sphere is first given a charge Q by bringing a charged object in contact with it. Then, the rotating sphere is brought in contact with the static sphere using the micrometer screw. Due to conduction, the charged static sphere now loses half of its charge, that is, Q by 2 to the other sphere. This happens because the two metal spheres are identical in size. Now, both the spheres are identically charged with a charge of Q by 2 each. They start repelling each other since like charges repel. The measure of repulsion is the amount of deflection or the angle through which the sphere attached to the rod is displaced. The static sphere is now discharged by grounding. To recharge the static sphere, the rotating sphere is brought in contact with the static sphere using the micrometer screw. Again, due to conduction, the spheres now have a charge Q by 4 each. As both the spheres are identically charged, they repel each other. However, the angle of deflection observed is lesser than the previous observation for charge Q by 2 on each sphere. Therefore, it can be concluded that as the charge on the spheres decreases, the force of repulsion between them also decreases. From these experiments with charged spheres at constant distances, it was concluded that the electrostatic force between two charges is directly proportional to the product of the charges. If the charges are Q1 and Q2, then electrostatic force F between them is proportional to Q1 into Q2. Let this be equation 1. Now, keeping the charge on each sphere constant, if the distance between the charged spheres is varied using the micrometer screw, the angle of deflection is found to be inversely proportional to the square of the distance r between the charges. Since the force of repulsion is proportional to the angle of deflection, we can say that the electrostatic force F between the charges Q1 and Q2 is inversely proportional to the square of the distance r between the charges. Let this be equation 2. Thus, according to Coulomb's law, the electrostatic force between two charges is directly proportional to the product of the charges and inversely proportional to the square of the distance between the charges. Hence, the electrostatic force F between charges Q1 and Q2 separated by a distance r is proportional to Q1 Q2 by r square. Let this be equation 3. A constant of proportionality K is used to get the equation F is equal to K Q1 Q2 by r square. Let this be equation 4. If the charges are separated in free space, that is, air or vacuum, the value of the constant K is equal to 1 by 4 pi epsilon naught, where epsilon naught is called permittivity of free space. Thus, the electrostatic force F is equal to 1 by 4 pi epsilon naught Q1 Q2 by r square. In SI units, the value of the proportionality constant K is approximately equal to 9 into 10 power 9 Newton meter square per Coulomb square, and the value of epsilon naught is equal to 8.85 into 10 power minus 12 Coulomb square per Newton meter square. Hence, F is equal to 9 into 10 power 9 into Q1 Q2 by r square. Using Coulomb's law, a unit charge can be defined as one that experiences an electrostatic force of 9 into 10 power 9 Newton when placed at a distance of 1 meter from another unit charge in free space. Let us now study Coulomb's law in vector form. Let the charges Q1 and Q2 be at positions specified by the position vectors R1 and R2 with respect to the origin O. The vector R21 is equal to R2 minus R1 joins Q1 and Q2. The force on Q1 due to Q2 is F12. The force on Q2 due to Q1 is F21. In vector form, we can express Coulomb's law as shown. If Q1 and Q2 are like charges, they repel. In this case, the product of the charges Q1 and Q2 will be positive. The unit vector R12 cap is given by equation 5. Here, the force F12 will be in the direction of the unit vector R12 cap. If Q1 and Q2 are unlike with respect to each other, the force F12 will be in the direction of the unit vector R21 cap as given in equation 6. Since unlike charges attract each other. In this case, the product of the charges Q1 and Q2 will be negative. The unit vector R21 cap is given by equation 7. According to Newton's third law, Q2 experiences an equal and opposite electrostatic force to the one experienced by Q1. Therefore, we can write F21 is equal to minus F12. Let us now consider a system of charges Q1, Q2, Q3 and so on till Qn, as shown in the figure with position vectors R1, R2, R3 till Rn with respect to the origin O. We know that electrostatic force, as given by Coulomb's law, exists between every pair of charges of the combination. To find the net force on any charge in such a system, we first calculate the electrostatic force on that charge by each and every other charge of the system. Then, the net electrostatic force on that charge is equal to the vector sum of the individual electrostatic forces on that charge due to every other charge of the system of charges. The individual forces are unaffected by the presence of other charges in the configuration. This principle is called the principle of superposition. For example, if the charge Q1 is considered, then, according to principle of superposition, the net electrostatic force on the charge Q1 is F1 equal to F12 plus F13 plus so on till F1n. Let this be equation 8. F12 is the force on the charge Q1 due to Q2 and is equal to 1 by 4 pi epsilon naught into Q1 Q2 by R12 square into R12 cap. R12 is the distance between Q1 and Q2 and R12 cap is the unit vector in the direction of the force F12. F13 is the force on the charge Q1 due to Q3 and is equal to 1 by 4 pi epsilon naught into Q1 Q3 by R13 square into R13 cap. R13 is the distance between Q1 and Q3 and R13 cap is the unit vector in the direction of the force F13. Proceeding in this manner, we obtain F1n is the force on the charge Q1 due to Qn and is equal to 1 by 4 pi epsilon naught Q1 Qn by R1n square into R1n cap. R1n is the distance between Q1 and Qn and R1n cap is the unit vector in the direction of the force F1n. Now, using F12, F13, F1n in the principle of superposition, we have F1 as in equation 9. Thus, net electrostatic force on Q1 is F1 is equal to 1 by 4 pi epsilon naught into Q1 into sigma I equal to 2 to nqi by R1i square into R1i cap. Let this be equation 10. To understand the superposition principle more clearly, consider the charge configuration consisting of charges Q1, Q2 and Q3 with position vectors R1, R2 and R3 respectively with respect to the origin O. F12 is the force on the charge Q1 due to Q2 and is equal to 1 by 4 pi epsilon naught Q1 Q2 by R12 square into R12 cap. R12 is the distance between Q1 and Q2 and R12 cap is the unit vector in the direction of the force F12. F13 is the force on the charge Q1 due to Q3 and is equal to 1 by 4 pi epsilon naught into Q1 Q3 by R13 square into R13 cap. R13 is the distance between Q1 and Q3 and R13 cap is the unit vector in the direction of the force F13. To find the net force F1 on Q1 due to the other charges in the system, we should apply the principle of superposition. That is, we should have F1 is equal to F12 plus F13 vectorially. This we can do by using parallelogram law of vectors as shown. Then the direction of F1 will be along the direction of the diagonal of that parallelogram. The magnitude of F1 will be equal to root over F12 square plus F13 square plus 2F12 F13 cos theta, where theta is the angle between F12 and F13. By knowing the values of the parameters involved, the net force F1 on Q1 can be calculated. Now, let us consider the electrostatic force between two electrons having a charge equal to basic unit of charge E, which is equal to minus 1.6 into 10 power minus 19 coulomb, and separated by 1 meter in vacuum. The magnitude of the electrostatic force between them, according to Coulomb's law, is given as Fe equal to 1 by 4 pi epsilon naught E square by R square, where R is equal to 1 meter. Substituting the values of the various parameters, we have the electrostatic force between the two electrons is equal to 23.04 into 10 power minus 29 Newton. Let this be equation 11. Let us now compare the electrostatic force between these electrons with the gravitational force between them. The gravitational force F between the electrons is G into M1 M2 by R square, where M1 and M2 are the masses of the electrons, which are equal to 9.1 into 10 power minus 31 kilogram each. Substituting the values of the various parameters, we have the gravitational force between them is equal to 552.34 into 10 power minus 73 Newton. Let this be equation 12. Dividing equation 11 by equation 12, we have the ratio between electrostatic and gravitational forces, and we can see that the electrostatic force is enormously greater than the gravitational force. Consider a charged particle with a charge q held at rest at the origin of an imaginary coordinate system. If we place a charge q0 at a point P near charge q and release it, then the charge q0 accelerates away from the origin. This acceleration is due to a force on charge q0. Now, let us remove charge q from the origin and reintroduce charge q0 at the same point P. Charge q0 does not accelerate now and remains at rest. This means that the force experienced by q0 is due to charge q. We say that since charge q0 is in the electric field of charge q, it experienced a force. An electric field is a region in which the influence of a charge is felt. Since charge q produces this electric field, this charge is called the source charge. Charge q0 is called a test charge as it is used to study the effect of the electrical field created by charge q. We can use Coulomb's law to calculate the force on q0 due to q. The electrostatic force on q0 due to charge q is F is equal to 1 by 4 pi epsilon naught q q0 by r square into r cap, where r cap is the unit vector along the direction of OP. Let this be equation 1. Now, if q0 is a unit positive charge, that is, Q0 is equal to plus 1 coulomb, then the electrostatic force as denoted by equation 1 becomes 1 by 4 pi epsilon naught Q by R square into R cap. Let this be equation 2. Equation 2 indicates the electric field strength or intensity of electric field E, which is the force on a unit positive charge acting at a particular point in the electric field. Therefore, the electric field strength due to charge Q at point P is E equal to 1 by 4 pi epsilon naught Q by R square into R cap. Let this be equation 3. Electric field strength E is a vector quantity pointing in the direction of the force on a unit positive charge at a point in the electric field. In SI, it is measured in Newton per Coulomb or Volt per meter. From equations 1 and 3, the force on the charge Q0 can now be expressed as F is equal to Q0 E. Let this be equation 4. Hence, we can write the electric field strength at P as E is equal to F by Q0. Let this be equation 5. The above equation is valid as long as the test charge Q0 is very small and its own electric field is negligible. Hence, at point P, we write the electric field strength E as F by Q0 limit Q0 tending to 0. For a given distance R from the source charge Q, the value of 1 by 4 pi epsilon naught is always constant, and hence E, as given by equation 3, will also be constant. Hence, the electric field strength E at any distance R from the source charge Q is independent of the test charge Q0. It varies with R cap and is inversely proportional to R square. The electric field at any point in the electric field is finite and is 0 only when distance R is equal to infinity. In the electric field of a positively charged particle, the electric field strength vector E at any point in the field always points away from the charged particle in a radially outward direction. The point charge Q0 will be accelerated in the direction of the electric field as it experiences an acceleration A due to the force due to the electric field, and the acceleration is expressed as A is equal to Q0 E by m, where m is the mass of the particle. In the field of a negatively charged particle, the electric field strength vector at any point in the field always points towards the charged particle in a radially inward direction. Here, the point charge Q0 in this electric field will be accelerated in the direction opposite to the electric field. The magnitude of acceleration of Q0 is the same regardless of whether the electric field is due to source charge plus Q or minus Q. For a charge Q, at all points on an imaginary sphere of radius r around it, the electric field strength will be equal in magnitude and will be equal to 1 by 4 pi epsilon naught Q by R square. There is a spherical symmetry with respect to the magnitude of the electric field strength E in the electric field of charge Q. Consider a region consisting of point charges Q1, Q2, Q3, Q4, and so on in air, or a vacuum with position vectors r1, r2, r3, and so on relative to the origin O. Let P be a point in this region. The net electric field strength E at point P is the superposition of all the electric field strengths E1, E2, E3, E4, and so on due to the individual charges. The net electric field strength E at point P will be equal to the vector sum of all the electric field strengths E1, E2, E3, E4, and so on. Then, E is equal to 1 by 4 pi epsilon naught into Q1 by R1 P square into R1 P cap plus Q2 by R2 P square into R2 P cap plus Q3 by R3 P square into R3 P cap, and so on. Here, R1P is the distance from Q1 to P, and R1P cap is the unit vector in the direction of Q1 to P. R2P is the distance from Q2 to P, and R2P cap is the unit vector in the direction of Q2 to P, and so on. The net electric field strength E can now be written as 1 by 4 pi epsilon naught sigma I1 to N Qi by RIP square into RIP cap, where RIP cap is the unit vector in the direction of the net electric field strength E. Consider a situation where charge Q is accelerating. Then, it produces electromagnetic waves, which propagate at the speed of light. Here, Q0 is also accelerating in the electric field of Q, and there will be a force on Q0 due to the electric field of Q. This force on Q0 due to Q is actually caused by the electromagnetic waves generated by the accelerating charge Q, and which travel from Q to Q0 at the speed of light. Thus, an accelerating charged particle is a source of electromagnetic waves. For example, electric current applied to a solenoid creates an electromagnetic field around it. Consider a region consisting point charges Q1, Q2, Q3 and so on in air or in vacuum, with position vectors R1, R2, R3 and so on relative to the origin O. Let P be a point in this region. The net electric field strength E at the point P is the superposition of all the electric field strengths E1, E2, E3 and so on due to the individual charges Q1, Q2, Q3 and so on respectively. Now, R1P is the distance from Q1 to P, and R1P cap is the unit vector in the direction of Q1 to P. R2P is the distance from Q2 to P, and R2P cap is the unit vector in the direction of Q2 to P. R3P is the distance from Q3 to P, and R3P cap is the unit vector in the direction of Q3 to P. The net electric field strength E at the point P will be equal to the vectorial sum of all the electric field strengths E1, E2, E3 and so on. Therefore, E is equal to 1 by 4 pi epsilon naught into Q1 by R1 P square into R1 P cap plus Q2 by R2 P square into R2p cap plus Q3 by R3p square into R3p cap, and so on. The net electric field strength E can now be written as 1 by 4 pi epsilon naught into sigma I equal to 1 to N Qi by RIP square into RIP cap. In many practical situations, electric fields are produced by continuous charge distribution on the surfaces of the bodies of finite size and not due to the charge distribution discussed earlier. A few examples of some practical situations are a line charge distribution, a sheet of charge, or a volume charge distribution. Since it is difficult and impractical to work with discrete charges in terms of the microscopic locations of the charge distributions, to evaluate the electric field at a point, we adopt a different approach. In such situations, the entire charge distribution is assumed to be made of infinitesimally small elements, and the electric field strength at any point in the electric field will be equal to the vectorial sum of the electric field strengths due to each such small element. Let us look at a line charge distribution of length L carrying a charge Q as shown. If we consider a small element of such a charge distribution having a charge delta Q and of length delta L, the linear charge density, lambda, of such an element is equal to delta Q by delta L, since it is the charge per unit length. The SI unit of linear charge density, lambda, is Coulomb per meter. It is a scalar quantity. If a line charge distribution is carrying a non-uniformly distributed charge, then its linear charge density, lambda, for an individual element is equal to delta Q by delta L. If a conductor of length L is carrying a uniformly distributed charge Q, then its linear charge density, lambda, is equal to Q by L. Now let us consider a sheet of charge carrying a total charge Q on a surface area A. In such situations, the electric field strength at an imaginary point P can be calculated by assuming the charge distribution to be divided into infinitesimally small areas, each having an area delta A and charge distribution delta Q. Surface charge density, sigma, is the charge per unit surface area. Therefore, surface charge density for an individual surface element is expressed as sigma is equal to delta Q by delta A. It is a scalar quantity measured in Coulomb per meter square in SI unit. If charges are non-uniformly distributed, surface charge density for an individual surface element is expressed as sigma is equal to delta Q by delta A. If the charges are uniformly distributed over the surface, then the surface charge density, sigma, is equal to Q by A. Now let us consider a volume charge distribution. Consider a volume V carrying a charge Q. Let us assume that the total volume is divided into a number of small elements, each of volume delta V having a charge delta Q. Then, volume charge density, or charge density, ρ, of such a volume charge distribution is defined as the charge per unit volume. Thus, ρ is equal to delta Q by delta V and is measured in Coulomb per meter cube in SI unit. It is a scalar quantity. If charges are not uniformly distributed, the charge density ρ for an individual volume element is equal to delta Q by delta V. If the charges are uniformly distributed, the volume charge density of the conductor is expressed as ρ is equal to Q by V. Now, consider the small volume element, delta V, of charge distribution carrying a charge delta Q. We know that the charge density ρ is equal to delta Q by delta V. Thus, charge on the volume element is then delta Q equal to ρ delta V. The position vector of the volume element, delta V, with respect to the origin O is R. Consider a point P in the electric field of the volume charge distribution, which is at a distance of R' from the volume element delta V. The electric field strength at point P due to the volume element is delta E is equal to 1 by 4 pi epsilon naught delta Q by R' square into R' cap, where R' cap is the unit vector in the direction of the straight line from the volume element towards the point P. This can be written as delta E equal to 1 by 4 pi epsilon naught into ρ delta V by R' square into R' cap. Now, the electric field strength E at P due to the total volume charge distribution is equal to the vectorial sum of the electric field strengths due to all individual volume elements. However, this is impractical as there would be many infinitesimal volume elements at varying distances from the point P. Hence, to obtain the electric field strength E due to the total volume charge distribution, we integrate delta E within suitable limits, A to B, under the assumption that the volume elements have very small volume tending to zero. Consider a point charge plus Q and its electric field. Let us introduce a unit positive charge at a point P1 in the electric field of Q. As both the source charge and the test charge are positive, this unit positive charge placed at point P1 follows the path P1A in the electric field due to the repulsive force on it exerted by the electric field of the source charge. Thus, path P1A represents an electric line of force or an electric field line. An electric field line represents the path followed by a unit positive charge in an electric field. Repeating this procedure for various points in the electric field, we obtain the electric field lines around the charge. Electric field lines are used to represent the electric field of a charge or a system of charges pictorially. In fact, the electric field lines follow the same direction as the electric field vector at any point in the electric field. As any electric field line is the path followed by a unit positive charge in an electric field. If we draw all the electric field lines for the electric field of the given source charge Q, the electric field lines appear as shown. One of the most important characteristics of electric field lines is that they help us estimate the electric field strength. The relative density or closeness of the field lines at different points gives an indication of the relative strength of the electric field at those points. The field strength is stronger at places having more crowded field lines than at places where they are less crowded. To illustrate this, let us now consider two regions, A and B, of same area placed normal to the field lines in the electric field. The field lines in region A are relatively closer than those in region B. The number of field lines passing normal to an area is proportional to the magnitude of the electric field strength at these points. This indicates that the strength of the electric field at A is greater than the field at B. As the electric field strength is stronger in region A and weaker in region B, the electric field shown is a non-uniform electric field as the field strength varies from region to region. To understand the dependence of field lines on area, let us understand the relation between the area of the element and the solid angle created. For this, first let us understand the term solid angle. Solid angle is a measure of a cone. When the intersection of a cone with a sphere of radius r is considered, the solid angle delta omega subtended by the area element is defined as delta S by r square, where delta S is the area on the sphere, which is the area element cut out by the cone. Let this be equation 1. Therefore, delta S is equal to r square into delta omega. Let this be equation 2. For a given solid angle omega, the number of radial field lines is the same. At two different points, say x and y, in the electric field, which are at distances r1 and r2 from the charge, we observe that the area of the elements subtending the same solid angle delta omega will be delta S1 equal to delta omega into r1 square at x and delta S2 equal to delta omega into r2 square at y respectively. The number of field lines, say n, passing normal to delta S1 and delta S2 is also the same. The number of field lines passing normal to a unit area is equal to the electric field strength E. Therefore, the electric field strength E1 at x will be equal to number of field lines per unit area at x, which is equal to n by delta S1 or n by r1 square into delta omega, using the value of delta S1. Let this be equation 3. Similarly, electric field strength E2 at y is equal to n by delta S2 equal to n by r2 square into delta omega. Let this be equation 4. If we divide equations 3 and 4, we see that the ratio of the electric field strengths at x and y is equal to r2 square by r1 square. Hence, we can conclude that the electric field strength due to a point charge varies inversely to the square of the distance from the charge. From equations 3 and 4, we see that even though the number of field lines n and the solid angle delta omega are the same at x and y, the electric field strength E, which will be equal to number of field lines per unit area, is proportional to 1 by r square, where r is the distance of the point from the charge q. Earlier, you have learnt that the electric field strength vector of a positive charge, say plus q, always points in a radially outward direction, and the electric field strength vector for a negative charge, say minus q, points in a radially inward direction. Thus, we see that the electric field lines for a positive charge diverge normally from the charge, and those for a negative charge converge normally towards the charge. Let us now visualize the electric field lines for a system of two positive charges, say plus q each. From the field lines, we can see a very clear picture of the repulsion existing between the system of charges shown. The electric field lines also help us in visualizing the electric field of a dipole consisting of charges plus Q and minus Q. We observe that the electric field lines for an electric dipole are continuous lines extending from the positive charge to the negative charge. From the field lines, we see very clearly the force of attraction existing between the system of charges in the dipole. Thus, we see that the field lines convey a very clear picture of the nature of the electrostatic forces existing in any system of charges. From these examples of various charge configurations, we observe the following properties of electric field lines. The tangent drawn to an electric field line at a point in the electric field gives the direction of the electric field strength E at that point. The direction of the tangent at a point indicates the direction of the force on a unit positive charge at that point, and hence it gives the direction of the electric field strength at that point. For the electric field created by a system of positive and negative charges, the field lines begin at the positive charge and end at the negative charge, since the field lines diverge normally from a positive charge and converge normally at the negative charge. For a single charge, they may start or end at infinity. Electric field lines do not intersect each other. If the electric field lines intersect each other, then at the point of intersection there will be more than one direction for the electric field, which is not possible. The number of electric field lines is proportional to the magnitude of the charge. The number of electric field lines is proportional to the magnitude of the charge. For a charge configuration of magnitude Q, if the field lines per unit area normal to it are, say, N, then for a charge of magnitude 2Q, the number of field lines passing normal to a unit area is equal to the electric field strength. Electrostatic field lines never form closed loops due to the conservative nature of the electric field, since the lines of force diverge from a positive charge and cannot converge at the same positive charge. For a uniform electric field, the electric field lines are parallel, equidistant, and unidirectional. For a non-uniform electric field, the electric field lines are not parallel. In a charge-free region, the electric field lines are continuous curves without any breaks.